everyone. Welcome to your first content video. In this video, you're going to learn about set and interval notation. And we're starting with this because we will use this notation throughout the course, so I want to make sure you have a good understanding of it. But let's start with sets. So first of all, a set is just a collection of objects. Now, those objects could be numbers or they might not be numbers, but it's just a collection of objects. Each object in a set is called an element. A set is named using a capital letter. And is written with its elements listed in braces, or sometimes I call them curly braces. So I've got two examples here of sets. We've got set A. The elements of set A are 1, 2, 3, 4, and 5. And then we have set C, where the elements are shirts, pants, shoes, belts, and sweaters. So the elements of set C might represent the items in your closet. Okay, and again, I'm just trying to highlight the fact that a set is just a collection of objects, so not always numbers. All right, these are some of the symbols that we use with sets. The first symbol stands for the empty or null set, so that would mean there are no elements in that set. The next symbol, which kind of looks like a sideways U, stands for subset. The next one, which does look like a U, stands for the union of two sets. So here you'd be looking for the elements that are in set A or set B. Our next symbol, which looks like an upside down U, stands for the intersection of two sets. So here you'd be finding the elements that are in set A and set B. And then our last symbol, which looks kind of like a funny E, is read is an element of. So you might see a statement like 1 is an element of set A, something like that. All right, let's look at some examples using these symbols. So we're given two sets. We have set A and set B. And we're going to start with some true or false statements. So the statement in number 1 says, 3 is an element of set A. Well, if I look at set A, 3 is there, so it is an element of set A, so that statement is true. Okay, number 2 is read, 3 is an element of set B. Well, if I look over here at set B, that would be false. I do not see a 3 there. Okay, number 3 is read, set B is a subset of set A. Well, because set B consists of the elements 4 and 5, and I find those also in set A, this statement would be true. B is a subset of A. All right, statement 4 says set A is a subset of set B. Well, that would be false because the elements in set A are 1, 2, 3, 4, and 5, and we do not find all of those elements in set B. Okay, now 5 and 6 are not true or false. We actually want to find these. So number 5, we want to find the union of set A and set B, which means we want to find the elements that are in set A or set B. So this one's pretty easy. We're just listing all the elements that we find in both sets. All right, number 6, we want to find the elements that are in set A and set B. This stands for the intersection of the two sets. So the only number that's in both sets is the number 4. Pretty easy. Okay, now, in this class, we're going to use what's called the real number system. And the real number system breaks up into subsets of numbers. So first of all, we represent the real number system with a capital R. And, real numbers are any number that can be found on a number line. Basically, I'm saying that it's a real number as long as it's not an imaginary number. Okay, now the real number system, or real numbers, have two subsets, irrational or rational. So irrational numbers, which we represent that set with a capital I, these are decimals that never end and have no pattern. So I'm talking about numbers like pi. There's another number e, which is a decimal that never ends and never repeats. Or anytime you're finding the square root of a non-perfect square, like square root of 2, for instance, will give you a decimal that never ends and never repeats. So these are some examples of irrational numbers. The other subset is rational. So rational numbers are all your fractions and decimals that end or do have a pattern. Now, we represent, since we've already used R for real numbers, we represent the set of rational numbers with a Q. So I like to think of that as Q for quotient, which, because a rational number is a fraction bar means to divide. This makes sense. So again, your rational numbers are your fractions, mixed numbers, decimals that end, or decimals that repeat. Okay, now rational numbers can also be represented with subsets. And those subsets are natural, whole, and integers. So I'm going to start at the bottom with natural numbers. We represent the set of natural numbers with a capital N, and your natural numbers are your counting numbers. So if you were trying to count how many of something, you would always start with the number 1. So your natural numbers start at 1 and then keep going. Okay, now the set of whole numbers, which is represented by a W, is your natural numbers, but just adding a 0 to the list. Because, over time, like, numbers kind of started with a need to be able to count how many you have of something, but over time, we realized we needed a way to represent nothing. Like, let's say you're counting how many apples are in the basket. Well, what if your basket is empty? How do you represent that? It led to the concept of 0. Eventually, we needed a way to represent less than 1, or, what if you have half of an apple? How do we represent half of an apple? And that led to fractions. Your integers came from a need to represent numbers below 0. So, I don't know, an example might be if you think about sea level. If you live above sea level, that would be a positive number. If you live below sea level, that's a negative number. Or if you think about your bank account, if you take out more than you have in your bank account, you end up with a negative balance. We can come up with a lot of other examples, but eventually we needed a way to represent negative numbers. So if we add the negative numbers to our list of whole numbers, then we have these sets of integers. But again, these are all considered rational numbers, okay? These are all subsets of rational numbers because natural, whole, and integers can all be written as fractions by just putting a 1 under it. We can even write 0 as a fraction by putting a 1 under it. We can represent negative numbers as a fraction by putting a 1 under it. So all of these, are underneath rational numbers because they are subsets of rational numbers. Okay, so let's look at some examples. Here we want to list all the subsets that the number belongs in. So for instance, 4 is a counting number. It's a natural number, right? Which means it's also a whole number, which means it's also an integer, which means it's also rational, and it is, of course, a real number. Okay, now, -5. Because it's a negative number, it's an integer, which is also rational, which is also real. Okay, 3/5, that's a fraction, that's a rational number, which is also a real number. Square root of 10, that's an irrational number, which is also a real number. So you just want to make sure that you identify all the subsets that this number might fall into. All right, let's talk about set builder notation. This is what set builder notation looks like. I know it can look a little confusing at first, but again, it's just a different way to represent a set of numbers instead of like listing each element in the set, which sometimes might be hard to do, you know, if we're talking about fractions and decimals. So this is just another way to write it. Now, this is how we would read this notation. We would say the set of all x such that, and then I just read the inequality, -3 is less than or equal to x, and x is less than or equal to 16. X is an element of the set of integers, okay? So, you know, that way we know that we're dealing with the numbers between and including -3 and 16, but we're also only talking about integers. Okay, let's look at some examples. We want to describe the set of numbers using set builder notation. And for these examples, I'm just going to use x as my variable, but it wouldn't have to be x. Okay, we might, let's say we're talking about range, we would use y. So here, you're always going to start out with the set of x such that, and then we want to put this into an inequality. So because these are numbers from 2 to 7, this would be a compound inequality. I would say 2 is less than or equal to x, and x is less than or equal to 7. But then I would want to establish that x is an element of the set of integers. Okay, now number 2 is easy because it's already an inequality. So all I have to do is start with my curly brace. X, so we're going to say the set of all x such that x is greater than -17. X is an element of the set of real numbers. Now, how did I know that? Well, if all we're given is x is greater than -17, then numbers greater than -17 are going to include all the rational and irrational numbers. Okay, greater than -17. Okay, for number 3, you know, these dots indicate that the numbers keep going in our set. So I want to say the set of all x such that, put it into an inequality, x is greater than or equal to 0. And I want to say x is an element of, now you have some choices here. You can either use whole numbers or you can use integers. I'm going to use integers just because I like it. But you could say x is an element of the set of whole numbers as well. All right, you guys, let's look at interval notation. Now, this is actually the notation we'll use the most in this class because it's a real easy way to represent inequalities by using brackets and parentheses. So we have 2 different types of intervals here. We have bounded and unbounded. So a bounded interval just has 2 endpoints, which are represented by A and B. Sometimes we include our endpoints in the interval, and sometimes we don't. Okay, so, you know, if we're saying like A is less than or equal to x, and x is less than or equal to b, this would mean that we would include the endpoints in our interval, and so we would want to use brackets to indicate that we are including the endpoints in the interval. If your inequality is just less than, then we're not including the endpoints, and so in that case, we would use parentheses. And then, of course, you might, you know, have a less than or equal to and a less than, like in my next example. So this is A is less than or equal to x. So notice that there's a bracket on the A, and x is less than b, so we'd use parentheses on b. And then in the last example, it's just switched around, parentheses on A, bracket on B. You guys probably remember when you were graphing inequalities, Like if I were to be graphing this first inequality on a number line, remember how you would use closed circles for less than or equal to? Same idea. Closed circles coincide with brackets. Open circles coincide with parentheses. Okay. You know, all of these would kind of look like this. A and B. Okay. Now, we also might have unbounded intervals. So unbounded intervals is where you only have one endpoint, and then basically your numbers are going to continue on forever, meaning to infinity, in one direction. So in this case, you only have one inequality, like x is greater than or equal to a. You know, if I were to graph this, again, it would be a closed circle, and then we would use an arrow pointing to the right. Arrow to the right means infinity. Because I'm using a closed circle, or because the inequality is greater than or equal to, I use a bracket on A. Now, we always use parentheses on infinity. Okay. Now, sometimes people get confused with the less than or equal to or less than. If x is less than or equal to a, again, if we were to graph this on a number line, a would be here. I'd use a closed circle on a, and then my arrow would be pointing to the left to indicate x is less than or equal to a. And when we have our arrow going to the left, you know, that's going towards negative infinity. Okay, because your number line, you know, 0 is in the middle, and it goes to infinity to the right and negative infinity to the left. So when you write your interval, you actually want to start with negative infinity, comma a. All right, and I see students switch that around a lot, but the correct way to write it is to actually start with negative infinity first, because we always read the number line from left to right, we read graphs from left to right, and we read intervals from left to right. Same idea with x is less than a. We're going to start with negative infinity. The only difference here, though, because it's less than, you know, that would be an open circle if we were graphing on a number line. So we want to use parentheses on the a and not a bracket. Okay, let's look at some examples. We want to write each set of numbers using interval notation. So the compound inequalities, I think, are pretty easy. If it's an and compound inequality, you know where x is right here in the middle. All you have to do is represent your endpoints, and then just figure out whether to use parentheses or brackets. So because it's less than or equal to on both numbers, I would use a bracket on both. Okay. All right, number 2, x is greater than -4. So again, if you find it easier, just sketch, you know, like we were graphing it on a number line. -4 is here. It would be an open circle and then an arrow pointing to the right. So in interval notation, this would be parentheses -4, comma, infinity, parentheses, close your parentheses. Okay, now number 3 is a compound inequality, but it's an OR type. So, you know, your AND type compound inequality, like number 1, these are the ones that like come together on a number line. Like if I were graphing this on a number line, it would look like this. The OR type are the ones where the arrows go in opposite directions instead of pointing towards each other. So to represent x is less than 3, you know, that would be an open circle, arrow pointing to the left. To represent x is greater than 54, greater than or equal to, that would be a closed circle, arrow pointing to the right. So in this case, we have to write 2 separate intervals, like 1 for each inequality. And to represent the or in the middle, we are going to use our symbol for set notation, and we're going to put a U in between. Okay, so in interval notation, this would be negative infinity, comma 3, parentheses, or using that U, bracket on the 54, comma infinity. Okay, now I wanted to throw number 4 in there because honestly, you guys, this is probably the easier way to do this, to represent x cannot equal number 2. If we were, let's say, graphing this on a number line, okay, let's say 2 is right here on our number line, we would put an open circle on 2, but then we'd have arrows going both directions. So to write that as intervals, you actually have to write 2 separate intervals. So we have to go negative infinity to 2, but use parentheses on 2, because we do not want to include the 2. U, meaning 4, 2 again with parentheses, comma, infinity. So by using the parentheses, we're excluding the 2, okay? All right, you guys, so that is set and interval notation. We will definitely practice this in class, and thank you for watching.